Hello everyone, welcome to Alchemy IAS Academy. So in this video, we are going to discuss one basic topic from science and tech, that is nuclear energy. Okay, so within this nuclear energy, we will try to discuss some portion, okay, some basic in this video. Okay, so let's see nuclear energy, that is in the science and tech. Okay, one of the topic, that is nuclear energy. So before going into the basic of nuclear energy, we need to know some aspects. Okay, so what are atoms? Okay, what are isotopes, like that? Some basics. If you understand, then this topic will become little bit easier. So first I'll discuss basics, then we'll go into the concept. Okay, so for example, so we know, right, different elements are there. Okay, so let me take one element or any atom. Okay, so let me take an atom. So what are there within any atom? So there will be nucleus will be there. Okay, so there will be nucleus. This portion is called as nucleus. And okay, in the periphery, okay, in the periphery generally we'll have electrons will be moving. Okay, in the periphery generally we'll have electrons, and within this nucleus, okay, nucleus is made up of both protons and neutrons. Okay, so any atom, this is the basic structure of any atom. So any atom consists of three major things, that is, first thing is electrons will be there, which are moving around this nucleus, and within nucleus we have both protons and neutrons will be there. Okay, so these are the three basic things that are there in any atom. Okay, so protons, neutrons will be there within this nucleus, and electrons will be moving around this nucleus. Is it clear? So now one more basic things we'll see. So for example, if I take any element, for example uranium or hydrogen or anything, if I take, okay, so there are certain basic things are there, like atomic number and mass number. Okay, every one of you had heard about this one when we are in the school, that is atomic number and mass number. So what are this atomic number and mass number? Let me take any element X. Okay, so any element X will have certain number of atoms will be there and certain number of mass number will be there. So what are these atomic number? Atomic number is nothing but it is the number of protons. Okay, so atomic number is number of protons and mass number is number of protons plus neutrons. Okay, number of protons plus number of neutrons is called as mass number, and this one is only talking about this atomic number is nothing but number of protons. Okay, so now let me take any element. Okay, so any element will have both atomic number will be there, atomic number will be there here, and here it is written mass number. Okay, so atomic number will be written here and mass number will be written here. Okay, so now based on this we'll have one more topic. Okay, so that is also a kind of basic only we'll see. After that we'll go to the actual concept of nuclear energy. So now we have understood that any element will be there, okay, which consists of atoms will be there. Okay, that is number, that is means that is number of protons will be there, that are called as atomic number, and mass number will be there, that is number of protons and neutrons. Okay, so that is mass number. Okay, for example, let me take one example of uranium, because uranium is of our concern when it comes to nuclear energy, right? So uranium, if I take, okay, so its atomic number will be 92 and its mass number, okay, different mass numbers will be there, like 235 will be there, or 238 will be there, or 233, like that different mass numbers are there. Okay, so if the element is same, okay, if the atomic number is same, okay, if atomic number is same, but if the mass numbers are varying, okay, if the atomic number is same, means the element is same. Okay, the element, that is uranium, that is common, but if the mass numbers are varying, for example, if I write like this, 92 uranium 233, this is one element. Okay, 92 uranium 235, this is one more. 92 uranium 238, this is one more. Okay, so in all these cases, if I see, the element is same. Okay, because the atomic number is same. Always remember, if atomic number changes, then the element itself will change. Okay, so if element is same, means the atomic number of that element will be same. Okay, so atomic number is 92 in this case, but mass number is changing, right? Such elements which are having same atomic number, okay, or otherwise I'll write here. So elements which are having, okay, I'll write here. Just a second. Okay, I'll write here elements or things which are having same atomic number but different mass number. Okay, elements which are having same atomic number but a different mass number, such elements are called as isotopes. Okay, what are those are called as isotopes? Isotopes are those elements which are having same atomic number but a different mass number. Mass number will be keep on changing. Okay, such elements are called as isotopes. And for example, here I told you, right, one of the isotope means these are all the isotopes of uranium, can I say? Okay, that is uranium 233, uranium 235 and uranium 238. Okay, these are the isotopes of uranium. The same way, when it comes to hydrogen also, there are different isotopes of hydrogen are there. Like this is 1H1, it is protium. This is deuterium. This is tritium. Because here, these are all the isotopes of which one? Isotopes of hydrogen. Okay, these are the isotopes of hydrogen. That is 1H1 is nothing but called as protium, deuterium, and tritium. Okay, so these are the isotopes of hydrogen. Similarly, isotopes of uranium. Right. So now we have understood there are different isotopes are there with respect to the uranium. So isotope is nothing but any element which is having the same atomic number but different mass number. Okay, so now let me go to the another topic. Okay, so for example, whatever the uranium that is there, when we excavate it from the ground surface, that is uranium ore, whatever that is there. Okay, so when we excavate that one, it is a natural substance, right? So when we take any natural uranium, okay, assume this is the natural uranium which we have excavated, right? So in this natural uranium which we have excavated, so this majorly consists of, okay, uranium 238 and uranium 235. Okay, so in natural uranium other things are also there, but majority of the portion, if I see, uranium 238 consists of how much? It is the major, it is a major portion. Okay, 99.3 percentage. Okay, whatever the natural, for example, if I take a 100 grams or 1000 grams, in that 1000 grams 993 grams consist of this only uranium 238, and this uranium 235 will be somewhere very close to 0.7 percentage. Okay, so disproportionately, if I say, uranium 238 will be in very high proportion and very less proportion of uranium 235 will be there. Okay, so uranium 238 will be very high in proportion and uranium 235 will be very less in proportion, that is 0.7 percentage only will be there. Is it clear? So in that case, why I was discussing this one is, there is one connected topic is there, that is any material that is used in nuclear reactor. Okay, generally there are different types of materials are there. Okay, so materials will be classified into, one is called as fissile material, and the second one is called as fertile material. Okay, so any material generally which is used in nuclear reactor, okay, there are classified into two types. One is called as fissile material, second one is called as fertile material. Okay, so what are these fissile materials? Okay, so remember, fissile materials are those materials. Okay, so fissile materials are those materials whenever we use in nuclear reactor. Okay, when we use in nuclear reactor. Okay, so these fissile materials will, okay, used in nuclear reactors is nothing but, for example, let me take one any material X. Okay, with example I will told, but for timing just understand. So assume when any material is bombarded with neutron, okay, or collided with neutron. Okay, so this material, whatever that is there, this material will be split into different some other materials. Okay, and in that process it will try to release some neutrons and then it will try to release some energy. Okay, so remember, I'll discuss with example also, but timing just remember, any material when it is bombarded with neutron, whenever it is bombarded with neutron, that material or that thing will split into different other materials, and in that process it will release more neutrons and then also it will release huge amount of energy, and this energy generally we will use in our nuclear reactors, and this energy is generally called as nuclear energy. Okay, whatever the energy that is released, okay, this energy is called as nuclear energy, and this energy will be used to heat the water so that it will convert into steam, and that steam will be used to run the turbines, and whenever turbines are running, so mechanical energy will be converted into electrical energy. Okay, so this is the mechanism generally will follow in this one. So but once, what is this fissile material? Fissile materials are those materials whenever it is bombarded with any neutron, it will split, and in that process it will release huge amount of energy. Okay, remember, huge amount of energy it will be releasing. Okay, so what are these fertile materials? Okay, so what are these fertile materials? So fertile materials are those materials whenever, okay, whenever we bombarded with any neutron, okay, whenever we bombarded with any neutron, so it will not split. Okay, it will not split into any different elements. Okay, here what is happening, it is splitting, and in that process it is releasing huge amount of energy, right? But in this case, okay, it is not going to split. Instead of that one, okay, there will be some changes will occur. Okay, for our exam that changes are not needed, but ultimately what is happening is, because of this neutron, okay, this element x, whatever that is there, that element x will be converted into element y. Okay, so this element x will be converted into element y, and as it is not splitting here, okay, it is just converting. Okay, that process is called as transmutation. Transmutation. Okay, so an element will be transmuted into another element. Okay, and there won't be any release of energy. Remember, there won't be no release of energy. Okay, remember, here it is releasing energy, and that energy is called as nuclear energy, which can be used to run the turbines and generate electricity. But here these elements are not splitting. Instead of that one, they are transmuted or converted into different other elements. And if you see here, this element, whatever that is there, right, this element, in majority of the cases, this transmuted element is there, right? This transmuted element is generally acting as a fissile material. Okay, so fissile material. Okay, means whenever, for example, okay, what is the meaning of this is transmuted into a fissile material? Meaning this y element, whatever that is there, if this y element is bombarded with any neutron, okay, if this y element is bombarded with any neutron, if it is a fissile material, what should happen to this one? It should split, and it should release neutrons, and energy also it should release, right? So because of this one, this fissile material, whatever y is there, it will split into different elements, and in that process it will release neutrons, and it will also release some energy, and this energy we will use for our nuclear reactors. So what is the meaning now of fertile materials? Remember, fertile materials are those materials whenever we bombarded with any neutron, it will not split to give energy. Instead of that one, it will be transmuted and forms into another element, and that element in general can be a fissile material. Means whatever the new element that is formed or transmuted, that new element can act as a fissile material. Is it clear? So this is the major difference between fissile materials and fertile material. Okay, so why I have discussed this one is, for example, okay, natural uranium, whatever that is there, this is there, right? So now you have understood, right? So in nuclear reactors, which material is our concern, or which material is our of interest? These fissile materials are our interest, because these are the materials which are converted into energy, right? Means they are splitted and they are giving energy, and these are not giving energy, right? So for our nuclear energy, okay, these fissile materials are very, very important. Is it clear? But if you see the natural uranium, okay, natural uranium, we have seen, right, this one. So in this natural uranium, uranium 238 is how much proportion? 99.3 percentage. And this uranium 235 is how much? Only 0.7. And if you remember, okay, please try to remember this one. This material, uranium 235 is there, right? This uranium 235 is fissile material. Okay, this uranium 235 is fissile material, and this uranium 238 is there, right? This is fertile material. Okay, always remember, uranium 238 is fertile material, and this uranium 235 is fissile material. But our interest material is which one? fissile material. Means fissile material is how much? Only 0.7. Very less amount of fissile material is there, right? But that fissile material is the important one for us for the generation of nuclear energies, right? So as this percentage is very less, okay, so the energy whatever that is generated, because if I use the natural uranium as it is in my nuclear reactor, will it be useful for us? No, right? Because this is the one which is generating energy for us, right? This is the one which is generating energy for us, and the one which is generating energy proportion is very less, and this one is the fertile material which is not generating any energy for us. Instead of that one, it will be converted into some other material, that is a fissile material. That equation we'll see. Is it clear? So now first we'll see the equations, but I think you have understood, right? So the useful material proportion is very less, and in a way the other material proportion will be little bit higher, right? So our job, what is our job? We need to, can I say, if I increase the proportion of this fissile material, okay, that is uranium 235, if I increase the proportion of this fissile material, can I say my nuclear energy purpose will be improved, because this is the one which is giving energy, right? So if I increase its proportion, then can I say that whatever the energy that is generated in my nuclear reactor will be a decent amount of energy, right? So that increasing the proportion of, okay, I'll write here, increasing the proportion, increasing the proportion of fissile material is called as, fissile material is called as uranium enrichment. What is this one? So it is the increasing the proportion of fissile material, okay, in the natural uranium. The increasing the proportion of fissile material is called as uranium enrichment. Okay, I'll discuss this uranium enrichment also, how we will increase the proportion of fissile material, that we will see. But before that one, we'll see some of the examples of fissile materials and fertile materials. So right now we have seen two examples, right? One is uranium 238. Okay, so this is a kind of fertile material, and this one uranium 235 is there, which is a fissile material. Okay, and its proportions also we have seen 99.3 percentage, and this one is 0.7 percentage. Okay, this is what we have seen, right? 99.3 percentage, and this is 0.7, right? So for example, if I take uranium 238, so uranium 238 means it is a fertile material, and we have seen earlier also fertile materials when they are bombarded with any neutron. Okay, when a fertile material is bombarded with a neutron, what will happen? It will be transmuted into some other material. Some changes will occur, no need what are the chemical changes that are occurring here. So this material directly will be transmuted. Just remember, this material will be transmuted and converted into another material which is called as plutonium 239. Okay, so whenever uranium 238 is bombarded with any fast moving neutron or any neutron, okay, remember any neutron, it is transmuted and finally converted into plutonium 238. And remember, this plutonium 238, already I told you, right? Whatever the material, that Y, earlier example I told you as Y, right? So that material is a fissile material. Okay, I told. So can I say this one is a fissile material is formed? Okay, what is the meaning of fissile material? Means if I take plutonium 239 and if I bombarded with any neutron, okay, if I take plutonium 239 and if I bombarded with neutron, what will happen? It will be splitting into some other elements, and then neutrons are formed, and in that process energy will be released, and this energy whatever that is there, it will be used to run the turbines, that is the nuclear energy. Is it clear? So can I write in the examples of this fissile, what is the second example of the fissile? That is plutonium 239. But can you tell me, plutonium 239 is naturally there or artificially we are obtaining from which one? It is artificially obtained from uranium 238. Okay, uranium 238, when it is subjected to any bombardment by neutron, it is transmuted and forming into plutonium 239. So this plutonium 239 is artificially made, and also it is a fissile material. Fissile material is nothing but whenever it is bombarded with neutron, it will split and it will form three neutrons and energy will be released. Is it clear? The same way if I see this uranium 235, because this is directly, so this is fast moving any neutron if I take, and it is uranium 235 because uranium 235 is a fissile material. So fissile material means it will split into different elements, and in that process 3 neutrons and energy will be released. Is it clear? So this is the normal mechanism that is happening. So some more examples are there. I'll discuss. Let me put it here. Okay. See here. There are some other materials are there like thorium. Thorium 232. Okay. So this thorium 232 is also the example of this fertile material. Okay. Fertile material is thorium 232. So I have told you two examples of fertile materials. So what are these two examples of these fertile materials? One is thorium 232 and second one is uranium 238. These are the two examples of the fertile materials. And what are the two examples of this what are the two examples of this fissile material? Okay, one is I told uranium 235 is one of the example, and the second example is plutonium 239, and one more example will be there, that is uranium 233 is there. Okay, this uranium 233 is also a fissile material. So there are three fissile materials are there, that is uranium 233, uranium 235 and plutonium 239. These are the three fissile materials, and two examples of fertile materials I have discussed, that is thorium 232 and uranium 238. So let me discuss about this thorium 232. So as we have seen, right? So whenever any fertile material, okay, fertile material is bombarded with a neutron, what happened here? Fertile material, when it is bombarded with a neutron, what happened? It is converted or transmuted into some other element, right? So similarly, whenever this thorium, which is a fertile material, I'll write here, this is a fertile material, and this one also I'll write here, fertile. Okay, and this one is fissile, this one is fissile. Okay, so whenever a fertile material is bombarded with thorium, some reactions will occur, and ultimately which one is forming here? Uranium 233 is forming. Okay, so whenever a thorium 232 is bombarded with neutron, it is forming uranium 233, and this uranium 233 is a fissile material. So what is the meaning of fissile material? We have seen, right? So what is happening in case of fissile material? I'll write here itself. Okay, so I'll try to. Okay, so I'll write here itself. So what is happening when any fissile material? Okay, what is this one? Uranium 233. When it is also a fissile material. When it is bombarded, then it will split into some other elements, and in that process, lots of energy will be released. Okay, so if you clearly see these three equations, okay, so these equations are generally seen in our nuclear reactor, which are responsible for what? These are responsible for release of energy, okay. So here fissile materials are the one, earlier also definition we have seen, right? Fissile materials are the one, whenever they are bombarded with any neutron, they will be split, and in that process they will try to release huge amount of energy. And we have seen two examples of fertile material, that is uranium 238 and thorium 232. These are the two fertile materials, and we know earlier definition we have seen, right? Fertile materials, whenever they are bombarded with any neutron, they will be transmuted and converted into different other elements, but there won't be any release of energy. So in this case, uranium 238 is a fertile material, is transmuted into plutonium 239, and thorium 232 is also a fertile material, which is transmuted into uranium 233, and these two, uranium 233 and plutonium 239, are a kind of fissile materials. Is it clear? So now, okay, so can I say the same way how plutonium 239 is not naturally found, that is artificially made, right? The same way, can I say uranium 233 is also artificially made by from the thorium 232? Okay, remember this one. Okay, both the plutonium 239 and even uranium 233 are artificially made. Is it clear? I hope you understood this basic concept. Okay, so this is the basic foundation. If you understand this one, our nuclear energy will be very, very easy topic. Okay, so I have told you, right, one more topic, like see this fissile material proportion. Okay, fissile material proportion, whatever that is there, it is very, very less in amount, fissile material. So I want to increase the fissile material proportion, and that is nothing but called as uranium enrichment. Okay, so uranium enrichment is a very important topic. Okay, already question have been asked in based on the uranium enrichment in the prelims. Okay, so let's see uranium enrichment. See, first we'll see what is the basic of that one, but there are different mechanisms are there where using that mechanisms we'll try to enrich the uranium. But basic understanding is that, for example, okay, so what is this one? Uranium 238. What is the proportion? 99.3 percentage, and uranium 235's proportion is hardly 0.7 percentage. And my job is, or my aim is, to increase the proportion of this fissile material. Okay, so my job is to increase the proportion of this fissile material, and that is nothing but called as uranium enrichment. So let's see how this uranium enrichment is made. Okay, to understand this one, I'll take one normal example. Okay, so normal example, for example, let me take uh, five, or let me take a box. Okay, let me take a box. Inside this box, okay, assume this one box is there. Inside this box there are some red balls are there. Assume total 6 red balls are there, and there are some white balls are there. Okay, 1 2 3 4. Okay, so how many red balls are there? 6 red balls are there. And how many white balls are there? 4 white balls are there. Okay, and how many red balls are there? 6 red balls are there. Okay, so if I take percentage wise, okay, what is the percentage of white balls and percentage of red balls here? 40 percentage. Okay, so I'll use some other color. So 40 percentage is of white balls and 60 percentage is of red balls, right? 60 percentage in this box, 60 percentage are red balls are there, and 40 percentage of white balls are there, right? So now assume, okay, just what we will do is, from this box whatever that is there, if I remove, okay, if I remove, assume, or before that, let us assume this one. Okay, let me discuss. Okay, let me say I have picked up 2 or 3, or let me take let me remove two white balls. 2 white balls are removed. Okay, so if I remove 2 white balls, so what is there in this box now? Okay, I'll maintain the red balls as it is. Okay, if I take now, okay, so what is the proportion of, or only 2 white balls are there? Okay, assume only 2 white balls are there, and take it like how many these balls are there? 1 2 3 4 5 6 balls are there. Okay, so 6 red balls are there and 2 white balls are there. So I'll write here 6 red balls are there, and how many white balls are there? Only 2 white balls are there. Okay, so only 2 white balls and 6 red balls are there. So now if I calculate the percentage, okay, so if I calculate the percentage, so will it be more, or what should be the percentage? Earlier the percentage of white balls, how much? It is only uh, hardly it is 40 percentage. Okay, now its percentage is 60. Okay, now if I see in this case, if I remove white balls, okay, so what is the proportion of white balls now? Its percentage will be reduced compared to the 40. So somewhere around, assume, let us assume, okay, why to do calculation, assume percentage has came down to around 33 or 30 percentage something. If that is there, 30 means definitely its proportion will be increased to somewhere 70 if it is 30, because its proportion is more, right? Is it clear? So because of this one, what is happening? As the percentage of any element, if I remove this one, then the opposite ones or the other elements percentage has been increased, right? So that is what the same technique will apply in case of our uranium enrichment also. For example, if I take, okay, so if I take okay, so in our case, uranium 238 percentage is more, right, and uranium 235 percentage is very less, that is 0.7. So by any chance, take it like by any chance, if I remove some of the uranium, okay, if I remove some of the uranium from this box, okay, or from this total ore whatever that I am getting, okay, so if I remove this one, so can I say it's proportion wise? Okay, assume, okay, assume you have removed out of this 99.3 percentage whatever that is there, out of that you have removed certain grams of weight. Okay, so assume you have removed somewhere around 50 grams. Okay, if I remove that 50 grams now, okay, after removing this one, if I calculate the percentage wise, if I see the percentage wise of this fissile material, that is uranium 235, will be increased, right? Because the other material proportion has been reduced. Because the same way we can see here, because assume this one is our assume these red balls are our fissile materials. Okay, if red balls are our fissile materials, if I remove some of the fertile material, that is white balls, because here also I am removing the fertile material, right? The same way if I remove the white balls here, okay, so the same way I have done here. So if I remove the white balls, what is happening? The proportion of red balls is increasing, but the quantity of red balls are increasing or same? The quantity of red balls is same. Okay, weight wise, if I see, whatever the weight of uranium 235, earlier it is there, 5, that is 7 grams is there, means the weight will be only 7 grams. Okay, its weight will not increase, but the percentage wise, okay, the proportion wise, it will increase. Always remember this one. So in uranium enrichment, I'll write in uranium enrichment. Okay, so percentage wise, that is proportion wise, okay, proportion will increase, but the weight of overall weight of fissile material fissile material remains same. Okay, remember this one. Okay, because here the earlier also 6 balls are there, now also 6 balls are there, but percentage wise if I see, it has been increased. Okay, but here also if I remove this fertile material, the proportion wise, percentage wise, it will increase, but weight wise it will always remain same. So this is called as uranium enrichment. It is nothing but it is the increasing the proportion of fissile material in the complex. Okay, that is uranium ore, whatever that is there. So in the natural uranium, if you try to increase the proportion of fissile material, then that technique is called as this uranium enrichment. Okay, so there are, based on the uranium enrichment, we have seen, right, naturally how much it is there, only 0.7 is there, right, enriched uranium. Okay, that is uranium 235 proportion is only 0.5 is there, right? So based on the enrichment, okay, so based on enrichment, there are different types of uranium enrichments are there. For example, low enriched uranium is there. That is, low enriched uranium is nothing but if the uranium 235 or fissile materials proportion, if it is less than 20 percentage. Okay, so if the fissile material proportion is less than 20 percentage, it is called as low enriched uranium. And there is one more thing is there, that is called as high enriched uranium is there. Okay, if the fissile materials proportion, okay, if the fissile material proportion is more than 20 percentage, okay, if it is more than 20 percentage, it is called as high enriched uranium. So there are two types of enrichments are there. One is low enriched uranium and one is high enriched uranium, based on the proportion of the fissile material. So if fissile material is less than 20, it is called as low enriched uranium. If the fissile material is more than 20, generally it is called as high enriched uranium. Okay, so if any high enriched uranium is there, okay, most of the times this high enriched uranium can be used for making of nuclear weapons. Okay, so if its proportion is increased to 30, 40, 50, 60, okay, 90, like that, more and more enrichment, the chances of making a nuclear weapon are very, very high. Okay, and this low enriched uranium water that is there, so it is generally useful for our energy generation. Okay, energy generation is nothing but also called as civil purpose. Okay, so energy generation is also called as civil purpose. Okay, that is low enriched uranium can be used in majority of the cases, somewhere around 5 percentage or 3.55 percentage somewhere of enriched uranium is used in our nuclear reactor for the generation of energy. No need of even going till 20 also. Even 5 percentage of enriched uranium is also sufficient to generate huge amount of energy. Is it clear? So till now we have seen certain basics. Okay, let me just rewind some basics. Okay, so let me show some basics here, whatever we have discussed till now. So first we have started with atom. So atom consists of nucleus will be there at the center, and this nucleus is made up of protons and neutrons, and at the periphery electrons will be keep on continuously moving. Okay, such things are called as atoms. And there are different elements are there, and there are different names are there, like atomic number and mass number is there. Atomic number is number of protons, mass number is number of protons plus neutrons, and any element consists of mass number and atomic number, right? So for example, I have taken uranium, right? Uranium has a different elements are there. Okay, those elements are called as isotopes. Isotopes are nothing but those elements which are having same atomic number but different mass number. Okay, I took the example of uranium, and uranium has certain isotopes like uranium 233, 235 and 238. And also hydrogen also I have discussed. Hydrogen has isotopes like protium, okay, deuterium and tritium. Okay, these are some of the isotopes of even hydrogen. Okay, so after that I have started with natural uranium, whatever we have excavated, that is having 99.3 percentage of uranium 238 and hardly 0.7 percentage of uranium 235. This is the natural uranium. Okay, so based on that one we have, okay, whatever the material that we are using in any nuclear reactor, two types of materials are there. One is fissile material, second one is fertile material. Fissile materials are those materials whenever we bombarded with any neutron, then it will try to split, and in that process it will try to give some energy. Okay, this is what you have seen. And fertile materials are those, okay, whenever we bombarded with any neutron, they will not split. Instead of that one, they will be transmuted and converted into some other element. Okay, so in that process no energy will be released, but whatever the transmuted element is there, right, in majority of the cases that will be a kind of fissile material. Okay, so this is what we have seen. And in this also picture we have seen that there are examples of fissile materials and examples of fertile materials also we have seen. For example here, okay, just let me, okay, so for example, examples of fissile materials we have seen here. So what are these fissile materials? There are three fissile materials are there. One is uranium 235, uranium 233 and plutonium 239. These are the three fissile materials that are there. And fertile materials are two materials are there, that are uranium 238 and thorium 232, right? So I have even written some equations also. That is, whenever fissile material is bombarded with neutron, they will be splitting, and in that process neutrons are released and also energy is released. Okay, whereas this fertile materials, whatever that are there, they will be transmuted into another fissile material, that is uranium 233 or plutonium 239. And these two are not naturally occurring, but these are artificially made in the laboratories. Okay, so after that I have discussed as uranium 238, which is a fertile material. Okay, and uranium 235, it is a fissile material whose proportion is very very less. Our job is to increase the proportion of this fissile material. Okay, so that process of increasing the proportion of fissile material is called as uranium enrichment. And I have told this example of balls in the box, how if certain balls are removed, then the proportion wise other balls percentage will increase, but not the number of that or weight of that will not increase. Okay, so if I see here, I told you, right? So even based on this uranium enrichment, there are different types of materials are there. That is, low enriched uranium is there and a high enriched uranium is there. Low enriched uranium is nothing but when the fissile material proportion is less than 20 percentage, it is called as low enriched uranium, and if it is more than 20 percentage, it is called as high enriched uranium. And this high enriched uranium is generally used for our nuclear bombs. Okay, that is nuclear weapons will use using this high enriched uranium, and this low enriched uranium generally used for this energy purpose, also called as civil purpose. Is it clear? So I hope you got some basic understanding of this nuclear energy right now. And the last topic what we will discuss is India's three-stage nuclear program. Okay. Okay. So India's three-stage nuclear program. Okay, so with this topic we will try to close this or we'll end this video. So India's three-stage nuclear program, why India went for three-stage? Okay, because we have seen, right, this uranium whatever that is there. Okay, in majority of the cases we are using uranium. Okay, so 238, uranium 235, right? So this uranium whatever that is there, the proportion of uranium ore that is present in our India is very very less. Okay, so very less proportion of uranium is there in India. Okay, less uranium is present in India. But whereas if you see, India has India has almost more than 20% of thorium resource of the world. Okay, so whatever the thorium that is there in the world, in that more than 20% of thorium is present only in our country India. So our purpose is that, so if I start increasing usage of this thorium, okay, then the dependency on the uranium will be less, because whatever the uranium, we are having very less uranium, right? So because of that one, we are importing. What we are doing, we are importing uranium. So we don't want to dependent on any other country for this energy, right? So if I starts using this one, okay, so then our dependency of imports of uranium can be reduced. Okay, so that is the major idea behind our India's three-stage nuclear program, because we have huge amount of thorium, and we have seen, right, thorium is a fissile material or fertile material. It is a fertile material. If this would have been a fissile material, then maybe we would not have gone for this three-stage program. But this is a fertile material. If it is a fertile material, means I need to convert this one, that is transmuted into which one we have seen, right? This thorium 232, whatever that is there, it is transmuted and converted into uranium 233, and we have seen, right, uranium 233 is a fissile material. So fissile material means I can use this one in my nuclear reactors to generate energy, right? So this is the idea behind which we went for this India's three-stage nuclear program, and this three-stage nuclear program was designed by the great person, that is Homi Jahangir Baba. Okay, in the early 1950s. Okay, he has designed this program thinking about India's energy security, and he has designed this program. Is it clear? So now let's see what are this three-stage nuclear program. So let me start. So let me take enriched uranium. Okay, let me take enriched uranium. Okay, that is a 3% or 5% of enriched uranium I'll take. But whatever the fuel, okay, for example, in our bikes generally we'll use, what is the fuel, either petrol, diesel sort of things we'll use, right? The same way in nuclear reactor, we need to have some fuel, right? Okay, so these are called as, what is this one? Fuel rod. Okay, fuel rod. Okay, this fuel rod consists of, okay, this fuel rod consists of uranium 238 and uranium 235. Okay, this fuel rod consists of, what are the two things? That is uranium 238 and uranium 235. Okay, so this fuel rod, whatever that is there, okay, consists of these things. Okay, so majority of the portion is made up of this one, and very less amount of this one is there, right? Even after enrichment, 5% enrichment means very less, right? Okay, hardly, if I take 1000 grams, it will be having very less amount, right? So around 50 grams will be there, and this one will be 950 grams will be there, right? That much very small amount will be there. So now this fuel rod, whatever we have taken, so the same equations, whatever that we have discussed earlier, this fuel rod will be bombarded with one neutron. Okay, this fuel rod will be bombarded with neutron. So if it is bombarded with neutron, what will happen here? Whenever it is bombarded with neutron, what is happening here? This uranium 235, whatever that is there, this uranium 235 will split, because it is a fissile material, right? So because of this one, it will split and it will form into three more neutrons, and energy will be released, and this energy will be used to run the systems, that is run the turbines and generate the energy. Okay, so this will happen. Okay, so whatever the uranium 235 atoms are there, or molecules that are there, they will be splitted and converted into uh, some neutrons and some energy, right? So what happens to this one? What happened? Because this same neutron can be bombarded even with this one also. So if it is bombarded with this one, what is happening? It is transmuted. It is transmuted and converted into, what is this one? Plutonium 239. Okay, so this is what happening inside our nuclear reactors. On one side, this fissile material, this fissile material is converted into some other materials, and then three neutrons are released and some energy will be released. On the other side, this fertile material of uranium 238 is transmuted and converted into plutonium 239, and we have seen this plutonium 239 as a fissile material, right? So what we are doing, this is our first stage nuclear program. Okay, this is our first stage nuclear program, where, okay, where, okay, so what is the waste? Okay, in this first stage nuclear program, what is the fuel we are using? Uranium 235 and uranium 238 we are using. See, within this one there are different types of nuclear reactors are there. that is pressurized heavy water reactor. Okay, so boiling water reactors. Okay, pressurized water reactors are there, like the difference are there. So that we'll discuss in a separate video. But time being, just first we'll complete this three-stage nuclear program. So in first stage nuclear program, we are using the fuel. Okay, the fuel rod which consists of uranium-238 and uranium-235. And remember, in our first stage nuclear program, generally we are using natural uranium. Okay, which one uranium we are using? Natural uranium we are using in this one. Okay, always remember we are using the natural uranium. Okay, and in this one, natural means this one will be 99.3% and this one will be 0.7%. Okay, proportion also we have seen, means this whatever that is there, it will be converted into some materials and energy will be released and transmitted into this one, right? So now after some time what will happen, whatever the weight or whatever the molecules of uranium 235 are there, they will be completely converted into some other material, right? So if they are completely converted into some material, means if this uranium 235 is over, means is there any chance of energy generation in my nuclear reactor? No, right? Because this is the one which is responsible for energy and this one is converted into some other element, but no energy will be released, and this proportion is very less. So if these particles have been completely splitted and energy is released, means after some time this entire uranium 235 will be gone from my fuel rod, that is completely converted, right, into some other elements here, right, and energy will be generated, right? So at that time, okay, what will happen is huge amount of this material is a waste material for me, this material also waste material for me, right? And some material is also formed, that is plutonium 239, right? So this entire thing is nothing but, let us take it as a waste. Okay, so from this waste material, or I can say instead of waste I'll use like output. Okay, in this output material, whatever that is there, can I say some element, assume this element is X, this element is Y. Okay, some element X is there. Okay, I'll change the color. So some element X is there and some element Y is there. Along with this one, plutonium 239 is there. Along with this one, this uranium 238 may not be completely converted into plutonium 239. Some uranium 238 can be left over. Okay, some uranium 238 will be left over, and this is the output of the first stage nuclear program. So what is the output of this first stage nuclear program? Some waste materials are there, along with this one uranium 238 and plutonium 239 are also present, right? So in this waste material, okay, some useful material is also there. For example, this plutonium 239 is there, it is a fissile material. So if I can extract that fissile material, can I use that one as a fuel in my nuclear reactor? Because it is a fissile material, so if it is used, means it will split and it will give energy, right? So this is what we have designed, that is in our second stage nuclear program. Okay, I'll just minimize the size here. Okay, so okay, so what is happening? So whatever this waste or output that is there in the first stage nuclear program, from this waste I'll extract. What I will do, I will extract useful material. Okay, I'll extract the useful material, and this process of extracting the useful material from the waste or output is called as reprocessing. Okay, this is called as reprocessing technology. Okay, so this is called as reprocessing technology. So the first stage output will be reprocessed so that useful products will be removed. So what are the useful products? This one is a fissile material I can use, and this fertile material also I can extract, right? So now whatever the waste material that is extracted, okay, so means from this one whatever the useful material is extracted, right, that useful material will be used as a fuel in the next stage. Okay, can I say the waste of first stage, okay, after extraction can be used as a fuel in the next stage? So let me show you how this will work. Okay, so let me move a little bit. So in the second stage, okay, in the second stage, what I am doing, I'll take once again the same fuel rod. I'll take, where this fuel rod now consists of the waste of first material or first stage, that is plutonium 239, okay, and that what is the other one, uranium 238, okay. So these are the useful materials from the waste or output of the first stage, right? So I will use that output of first stage after reprocessing and use that one as a fuel rod, okay. So this will be the fuel rod for my second stage. So we know, right? So if it is a fuel rod for the second stage, okay, so if it is a fuel rod, the same way now I'll bombard with my neutron. So if I bombard with neutron, what will happen? This is a which material? This is a fissile material. So if it is a fissile material means it will split and then it will release neutrons and then it will give some energy. Is it right? So what will happen to this uranium 239? This 239 once again will be transmuted. This transmuted because it is a fertile material. It will be transmuted into which one? Once again, plutonium 239. So can you see, okay, one peculiarity in this one? On one side, this fuel, whatever we have used, that is fissile material, plutonium 239 is converted into some other elements and energy is released. Okay, means on one side, can I say with the time this plutonium 239 particles will be reduced from the fuel rod. Okay, that is what happened in the earlier first stage also, that is fissile material of uranium 235 has been reduced. The same way here also this will be reduced, okay, with the time. But can you see, if even though on one side plutonium 239 is reduced, but on the other side this uranium 238, whatever that is there, it is generating huge amount of plutonium 239. Can I say? So in this second stage reactor, okay, on one side, can I say on one side this plutonium 239 is consumed, but on the other side more and more plutonium 239 is produced. So can I say on one side some fuel is consumed, but on the other side more and more fuel is generated. Can I say that one? So such reactors, okay, such reactors are called as breeder reactors. Such reactors are called as breeder reactors, and India's second stage and even third stage are also breeder reactors. Anyway, I'll discuss that one. Okay, but timing, I think you have understood, right? Because on one side some fuel is consumed, but on the other side more and more fuel is breeding. Okay, that is more and more fuel is produced. Okay, so can I say, okay, as more and more fuel is produced, okay, such reactors are called as breeder reactors. And now can I say this one? Can I say, so whatever this one output is coming, so what is the output in this case? Once again, I'll take X and Y. So some X material is there and some Y material is there and some plutonium 239 I'm able to generate. Okay, along with this one, entire uranium 238 may not be converted. Some uranium 238 can also be there. So can I say whatever the output I'm getting, can I use the same output in this second stage? And means whatever the output is there, I'll reprocess that one and I'll use the same output here as a fuel in the second stage also. So can I say this will be continuously a kind of cycle can happen, right? So this is what we are doing in the second stage, okay. But there is some more addition is there with respect to the second stage. So this is the brainchild of our great person, that is Homi Jahangir Baba. So what we are doing is, after generating enough amount of plutonium 239, because we are generating more amount of plutonium 239, right? So after generating, okay, I'll write here, after generating enough amount of plutonium 239, okay, so what we are doing is, we already discussed, right? We had huge amount of thorium, right? So we want to use our thorium reserves, right? We don't want to dependent on any other person, right? Any other countries. So what we are doing is, in the second stage itself, after generating huge amount of or certain amount of plutonium 239, what we are doing is, so this is the fuel rod in the second stage, that is plutonium 239 is there on one side, on the other side uranium 238 is there, right? So this is the fuel, because in the recycling I'm using the same one as a fuel rod, right? So now what our Homi Jahangir Baba told is, so we will try to put a layer, okay, we'll try to put a layer of thorium 232, okay. So in the second stage only, after some period of time, we'll try to add a layer of thorium 232 also to this fuel rod. So now what will happen in the second stage itself? See here, Now if it is bombarded with neutron, okay, in the second stage, if it is bombarded with neutron, so what will happen? What will happen to this plutonium 239? It will split and it will try to generate energy. So this is the same cycle, and this one also, it will be transmuted and converted into what is called as plutonium 239. Okay, the same process, nothing change will be there. But what happened to this thorium 232? We have seen earlier one equation, right? Okay, so what will happen? Is a fissile or fertile material? It is a fertile material, and we know when a fertile material is bombarded with any neutron, it will be transmuted and converted into some other fissile material. So what is the material it will be converted into? Starting we have seen some equations, right? So this thorium 232 will be converted into what is this called? Uranium 233. Okay, so this thorium 232 will be transmuted into what is the element? That is uranium 233, and we know what is this one? This one is a fissile or fertile? It is a fissile material. Is it clear? It is a fissile material. So can I say the stage, in the second stage, ultimately, okay, whatever plutonium 239 is generating from here, the same plutonium 239 I will be recycling and I will be reprocessing and I will use here. And if I add thorium 232 after certain cycles, then I will start generating which one? Uranium 233, which is also a kind of fissile material. And this uranium 233, whatever that is occurring, okay, so this, whatever this is there, I will try to reprocess and I will try to extract this uranium 233. Okay, so this, because entire thorium may not be converted, right? So, and if entire thorium may not be converted means, in the waste, okay, of the second stage, okay, what I will get? Some uranium 233 will be there, and along with that some thorium 232 will be there, right? So these two materials, that is thorium 232 and uranium 233, will be used as a fuel for my third stage. Okay, so that I'll use as a fuel for my third stage. So what is the meaning of this one? So now I'll write here third stage nuclear, okay, program. So what we are using the fuel, the whatever the waste that is occurring, that is the fuel rod will consist of now uranium 233 and thorium 232. Okay, so the waste of second stage is used as a fuel in third stage. So can I say the waste of first stage is used as a fuel in the second stage, and the output of the second stage is used as a fuel in the third stage? So can I say we are using a recycling, a reprocessing, right, and using the same waste as a fuel in the other stage, right? So such cycles or such usage of nuclear fuel is called as closed closed fuel cycle. So our nuclear program is a closed fuel cycle where the waste of one stage will be used as a fuel in the second stage. Okay, anyway, we'll see here. So in the third stage, what will happen? Earlier, that's why earlier I have drawn or discussed that equations, because if you understand that equations, this nuclear stage program will be very easy. So for example, once again, if I bombarded this one with a neutron, okay, what will happen? So this is a fissile material and this is a fertile material. So what will happen to the fissile material? It will split and it will try to release some neutrons, and in that process it will try to release some energy, right? The same way, what is this one? Fertile material. What will happen to the fertile material? It will be transmuted. It will be transmuted into which one? Uranium 233. So can you see the same peculiar thing here? On one side, uranium 233 is consumed, and on the other side, uranium 233 is produced once again in the third stage also. That's why earlier also I told, even our third stage is also called as a breeder reactor. Breeder reactor. In the second breeder reactor, more and more plutonium is released, and in the third stage of our reactor, it is also breeder reactor where more and more uranium 233 is released, and this uranium 233 can I say can it be recycled and once again used as a fuel here, because we have already huge amount of thorium is there. So whatever the waste that is obtaining in the third stage, I'll extract that useful product, that is fissile material of 233, and I'll mix with thorium reserves whatever that are there in the country, and can I continuously run my third stage nuclear reactor, so that no need of India to dependent on any other foreign countries for the import of uranium. Is it clear? So this is the three-stage nuclear power program, which is a closed fuel cycle. So ultimately, I'll just briefly summarize these things, okay, in three-stage programs in a single picture. So in the first stage, okay, so this is the first stage. So what is the fuel we are using? Natural uranium I'm using. Natural uranium I'm using. So natural uranium generally consists of uranium 238 and uranium 235. Okay. So and this will be bombarded with neutron, and ultimately what is happening? This will be converted into plutonium 239, and this will be formed into different other materials. Okay. So whatever the useful material, that is, I'll do reprocessing. Okay. So I'll do reprocessing and I will extract the useful material. So what is the useful material that ultimately I'm getting here? Uranium 238 and plutonium 239 I'm getting from this. Okay. So output or from this waste, whatever that I'm getting, that is after reprocessing, I'm getting this one, and this one will be used as a fuel in my second stage. Okay. So in second stage, I'm using this one as fuel, and we know whenever it is bombarded with a neutron, once again, what will happen? This uranium 238 will be converted or transmuted into plutonium 239, and this one will be split and it will give energy. Okay. It will give energy. So in this case, more and more plutonium 239 is generated. So that's why it is called as breeder reactors. Breeder reactor. And after certain time, okay, after generating some amount of plutonium 239 in the same second stage, okay, in the same second stage, what we are doing, okay, so we will be adding a layer of thorium 232 along with that normal whatever this plutonium 239 is there, along with that uranium 238 we will be using. Okay. So now the same in the second stage, if I bombarded this one, then this thorium 232 whatever that is there, it will be converted into uranium 233, and this plutonium 239 will be consumed and energy will be generated, and this uranium 239 will be generating huge amount of plutonium 239. Okay. So from this one, okay, from this second stage waste, okay, I will try to reprocess it, and so that what is the output I am getting here? Output whatever that is there, that output is consisting of which one? Uranium 233 and then thorium 232, because this plutonium I'll recycle and use here itself, but whatever the waste that is occurring, this waste I'll extract, and this waste of uranium 233 and thorium 232 I'll use as a fuel in third stage. Fuel in third stage. So what will happen as a fuel in third stage? Uranium 233 is there and thorium 232 is there. Whenever it is bombarded with neutron, what will happen? This uranium 233 will split and it will give energy, and then this thorium 233 will be transmuted and converted into more uranium 233, and the same uranium 233 will be extracted, and this will be recycled and used in our third stage continuously. Okay. So this is the connection. Okay. So if you can see, okay, this is the third stage, this is the third stage, and this is the second stage, and this is the first stage. Okay. In second stage we have two cycle sort of things are there. So ultimately our job is to use our huge thorium reserves and convert that one into uranium 233 and use that as fuel, because it is a fertile material, sorry, it is a fissile material. So use that fissile material in third stage, okay, along with the fertile material thorium 232 which is there in India. Okay. So this is our complete three-stage nuclear program, which was designed by our homie Jahangir Baba in 1950s itself, thinking about India's energy security in the future. Okay. So but if you still say in majority, if you see it has been almost designed more than 70 years. Okay. But still, okay, India has been stuck in the first stage itself. Okay. So recently only we are slowly shifting into the second stage, but in majority of the nuclear reactors whatever that are there, we are still majority of nuclear reactors are working on the first stage itself. Okay. We just recently started entering into the second stage. Okay. Experimental reactors, okay, our prototype fast breeder reactors are there. Okay. So they are working. So I hope you got a decent understanding about, okay, India's three-stage nuclear program, and the reason why we adapted to this one also we have understood, that is majorly the occurrence of uranium and thorium reserves. Okay. Based on that we have went for this three-stage nuclear program. Okay, so I hope you have got a brief idea about the basics and also the three-stage nuclear program. So if you don't understand, just once again watch this video so that you will understand the basics and remember those equations whatever I have discussed earlier. Okay, so all the very best for your exam. Thank you.